In the last video, we saw that the central limit theorem for sample means shows us that the distribution of the sample means will create its own shape, center, and spread. Now, the shape will be normal, even if the original distribution was not normal. We'll talk about that. The center will be the center of the actual distribution, which is mu, so that's the easiest part. And the spread will become something new called the standard error. The standard error is SE of x bar, or sigma sub x bar, which is sigma divided by the square root of n, which means the larger your n is, the smaller your standard error is. So bigger sample sizes leads to less spread. Because n is in that denominator, you'll be dividing by bigger numbers with larger n, smaller numbers with smaller n. Now we need to talk about the conditions for which this holds true, because it's not true all the time. It's only true if we have these three conditions up here. So suppose you're taking from a population of size capital N, whatever that might be, you're going to take a sample of size little n. And in that population, there was a mean mu and a standard deviation sigma, right? So mean mu, standard deviation sigma, right? Those things were valid and existed. And you're going to take a sample of size little n from that. Well, there are certain properties that sample has to have in order for this to work. First of all, the sample has to be random, right? So every observation that you collect has to be random. Why? Well, because if it's not random, then you have bias problems that we talked about in section 1.5, right? And if your data is biased, then your whole everything's biased, and you have to throw out all of the work that you would do. So let me write that up. All right, so that's why it's so important that it's random. So that's condition number one. We kind of really can't do anything in probability and statistics if we don't have randomness, because if you don't have randomness, you have bias, and if you have bias, then everything would be invalid. Another thing to note is that a lot of our formulas are built upon probability ideas, and probability assumes randomness, right? So you can't use normal CDF or binom PDF or inverse norm or any of those things if you don't have randomness. So we have to have randomness because probability is the mathematical modeling for randomness. And so if you don't have it, then you're in trouble, right? Okay, so that's why condition one is so important. Now let's look at condition two. All right, condition two is talking about independence. So let's go back and look at it. It says if the observations are independent of each other, that's the condition, right? It has to happen. Now, if the sample is collected without replacement, then the population must be at least 20 times larger than the sample size. Okay, so let's scroll down a little bit and see what we mean. And I'm going to illustrate what this whole thing is talking about, this second sentence right here, in that next page, right? So I'm going to give it kind of a pink highlight. But the deal is that they have to be independent of each other. That's the actual condition. And then the second part is just a little caveat about how you can make this happen. Notice it's talking about without replacement, because if it was with replacement, you wouldn't worry about it, because with replacement is of course independent. Let's look at our example. So suppose you have a bulk bin at a large candy store, and it has 2,500 plain regular color M&Ms. So you've walked by them in the bulk aisle occasionally. You see that giant bin full of M&Ms and you think, who's going to notice if I just take a couple and pop them in my mouth? That's what we're talking about here. So suppose that we somehow know that in this 5-pound bin of M&Ms, there's 500 candies in there that are orange. And you're going to reach in and you're going to take 2 M&Ms at random. So now, why are those colors of those 2 M&Ms dependent? So they truly are dependent. Why? Well, because when we draw one M&M, it affects what's left in the sample or left in the bin to be drawn for the next M&M. Right? So drawing that first candy affects what's left in the bin, and there's only $24.99 left for the next draw. So now let's find the probability that both of them are orange. So that means that I want to draw in and have the first M&M be orange and the second M&M be orange. Now keep in mind there are 500 orange candies in the bin altogether. So the probability of the first one is orange. This is the general multiplication rule that we learned in section 5.4. So the probability the first one is orange and the second one is orange is the probability the first one's orange times the probability the second one's orange, given that, there's that slash, I know the first one's orange, which sounds more complicated than it is. Look, there's 500 out of 2,500 for that first M&M. So there's 500 orange ones out of 2,500. Then you assume you have that orange M&M, and you say, okay, well, then there's 499 orange ones left out of 2,499 M&Ms left in the bin. And I just use my calculator to find what those numbers are. And of course, that's atrocious. So I'm just going to use the lovely calculator and get an answer of 0.039936. So that's the probability that both of them are orange. All right. Now, what is the sample size and what was the population size? So that is, what is N, what is capital N, and what is N, sorry, is how does N compare to 0.05 capital N? All right, so the sample size is little n, which is 2, right? You're only taking 2 candies from this bin. So there's that number. The population size would be capital N, which is how large a bin are you drawing from? Well, you're drawing from a bin of size 2,500. So capital N is 2,500. So there's your sample size, there's your population size. So now let's check little n and 0.05 capital N. So 0.05 capital N is the next thing we want to know. Is little n less than or equal to 0.05 capital N? Right? That's what we're asking. All right, well, little n is 2. Capital N is, or 0.05 capital N is 0.05 times 2,500. So let's see if we can do it this way. All right, so this is the question we're asking. Is little n less than or equal to 0.05 capital N? Well, 0.05 capital N is 0.05 times 2,500, which is 125 with a calculator, and 2 is less than that. So yes, 2 is less than 125. Therefore, little n is less than 0.05 capital N. All right, so now we're going to use that. So let's assume that they were independent, which is a big assumption because we proved up above that they're actually not independent. They're truly dependent. When you pull that first M&M, you are affecting what's left, not by very much, which is kind of the point of all of this. So let's assume that they were independent. What would that do to the probability? Well, the probability then would just be the regular multiplication rule. It'd be 500 over 2,500 times 500 over 2,500, which gets you 0.04. But notice how similar these numbers are. It being different, dependent, right? We use the general multiplication rule up here. It gave us an answer that was just a tiny bit different, like really tiny bit different to what it would be if we assumed independence. And this gets to the moral of the story, which is what we've kind of written down here in this box, which is you can sort of fake independence, right? Since 2 is so small in comparison to the 2,500, those probabilities are barely different from each other. And that means that we can kind of fake our way to independence and say, yeah, it's close enough to independent that it doesn't really matter. It's just easier to calculate that. The answer for D, this one right here, this was way easier to calculate. It says it uses the multiplication rule for independent events. It's just simpler. Everything's nice. And that's the moral of the story, right? That's what I really want you to get out of this, not the probability portion, but the fact that hey, if you're taking a small enough sample from a large enough group, then it doesn't really matter if they're truly independent or not. You can sort of fake your way to independence, right? As long as you're taking a sample that is less than 5%, that's our rule of thumb. So we're going to go with 5%. So as long as our sample size is less than 5% of our population size, it's close enough to independent that the difference in the probabilities doesn't matter enough to us to worry about. So as far as we're concerned, 0.0399 and 0.04 are close enough to each other that it's just not worth our effort to make them different. So we'll just assume independence right here. We'll assume that independent from now on, as long as our little n is less than 5% of our capital N. And when you think about this, every little kid in the world knows this. Because if you walk, oh, and my dog does too, right? So if you walk my dog into the Pet Supplies Plus store, they put those doggy treats right down where she can get to them. And she just very quietly will grab one and kind of put it in her mouth because she's thinking, if I take one, no one will notice. It'll be fine, right? Little kids are the same way with candy. If you walk a little kid by a candy aisle, they'll be like, oh, if I just put my hands in there and take a few M&Ms, who's going to notice, right? It's the same deal, right? It's not enough. They're not taking enough in one little handful and one little mouthful for it to be worth your while to bother trying to figure out the difference. And that's what I mean by faking independent. It's like, it's not truly independent, but it's close enough that we're fine. Keep in mind, this is only true for if it's without replacement. If it's with replacement, let me make a note right here. If we have replacement, then we really don't have to worry about it. Then we automatically have independence. And that's an important little thing to note for your project, possibly, and amongst other things, which is if you're taking the sample with replacement, then this whole rule of thumb that's listed up here doesn't matter, right? This is only for without replacement. Because with replacement, you automatically have independence because of randomness being condition number one, right? Since it's random, you have the randomness covers your independence, right? The only way you can make it not independent then is if you biased yourself. So as long as you have random and it's unbiased, then you're fine. The only time you have to worry about independence is if you're sampling without replacement, which we will actually do a lot for like polling and other things, right? When you call people up to ask them questions, you have to pay a little bit of attention to independence. But if you're sampling with replacement, like dice or coins, that kind of thing, well, then you don't ever have to worry about it. It's automatically with replacement, therefore it's automatically independent.